Thank you so much for coming to the Microlensing breakout session. My name is Somayeh. I'm the coordinator of the Microlensing subgroup of TDS, and I'm sharing this session with Natasha and Katarzyna for sitting here. And so you've probably seen these slides a lot this week. I'm just going to quickly review that in case you have new people joining us. And so as you know, we have all agreed to abide by the code of conduct for this workshop. So if you witness or experience any violation of the code of conduct, please contact any of these contact names that you can see here. And please check out these to see if you are seeing any of these stickers on people's tags. And this shows how much comfortable it would be with shaking hands. And if you would like to wear a mask, you can, of course. And some people might have these pins, which is showing the amount of social battery they have at the time and how much they're comfortable socializing. So please be aware of that too. And the virtual participants, please keep muted when you're not speaking. And the in-person participants, I think we don't need a microphone here, but the virtual participants, please, if you have a problem hearing us well, please let us know, and we can repeat the question from here if it's better heard. And so we do have a Slack space for this session. You can put questions there, and we can continue the discussion after that. And so on Zoom, if people on Zoom, if you have any questions, you can use the raise hand option and unmute yourself or put the question on chat or on the Slack channel. So here's the session schedule. In this session, we'll have 5 talks. The first 4 talks in the first session are given by the members of the Microlensing subgroup on the various projects they've been working on. And after the first 4 talks, we'll have 10 minutes for Q&A for the first 4 talks. And in the second session, we will be focused on crowded field photometry. That section will start with a talk by Colin on DMS status on crowded field testing, and it will be followed by a discussion on the crowded field photometry. Okay, so our first talk is by Katarzyna. Katarzyna, do you want to?
I uploaded my slides.
Okay, good.
The thing, and it's a PDF.
Yeah.
Oh, and I think if we stand here, people on Zoom will hear us well.
Oh, okay.
Is that true?
Okay, so just keep that in mind. As long as you're close to these microphones, you'll be heard, and you can ask questions.
Yes.
Okay.
Is that okay? Should I like?
Do you want to make it? I don't know.
Sorry, so.
Is
there a way to make it bigger?
Let's see on the view here. Well, I can download it. And,
sorry.
Okay.
You need help.
Oh, we figured it out.
Yeah, I think we figured it out. Thank you so much.
Okay.
So I'm going to show you the.
Sorry, you need full screen, not show slideshow. Or slideshow will just automatically tick through. It'll like auto advance the slides.
Oh.
So if you go back out and you press enter full screen, or apparently you've stopped it somewhere. Fair enough. So view, enter full screen. Won't risk just skipping on.
Thank you so much.
Thank you so much. Okay, so I'll try standing here. Sorry for making this difficult for Somayeh. So, welcome everyone. My name is Katarzyna Kruszyńska. I'm a postdoc at Las Cumbres Observatory, and I would like to talk to you about the lessons we learned with our project as a pathfinder for follow-up for LSST alerts. So this is a microlensing session, so I will give a short, maybe I should sound like this. I will give a short reminder on what microlensing is. It's an effect of Einstein's general relativity, where we have a massive object, a lens, which is passing a line of sight between the observer and the luminous source. And because it's massive, it distorts space-time, and the image of the source, instead of being like a single object, it becomes split into 2 or more images. And when on galactic, on Milky Way scales, when the lens is moving in and out of line of sight, it creates a very characteristic bell-shaped curve. And it is important, microlensing is important because of the point that I will make now. As I mentioned, the lens only has to have mass. And with LSST and any other surveys, what we can observe is this, basically. It's all of the luminous sources in our Milky Way and beyond. However, there are 3 classes of populations that are very important and can be uncovered with microlensing, which are brown dwarfs, exoplanets, and compact objects such as black holes. These are the scientific drivers behind our project, Omega Q project, which is to find these hidden populations in the Milky Way. And LSST will be an amazing discovery engine for that, because it will provide multi-band photometry very deeply, up to 33 magnitudes in the galactic plane, which is an unprecedented depth, and it will cover a wide area of galactic plane. However, LSST has a relatively low cadence for microlensing events, especially for short time scale events such as brown dwarfs or exoplanet events, and we need a follow-up observations to fill in the gaps. This is where the Omega Key project comes in. It's a flagship project of Las Cumbres Observatory, which is a network of robotic telescopes. It is a multi-facility follow-up project with 2 classes of telescopes. We have been awarded hundreds of hours on them. And currently we are in the 2nd incarnation of this project, which is led by Rachel Street. And we have expanded our scientific goals from not only to cover exoplanets, but also brown dwarfs and black holes. In order to facilitate our research, or even actually do it, we need something which is called a target and observation manager. In our case, it's called the Microlensing Observing Platform, or MOP, and it is an intermediate step between the surveys and alert brokers and the facilities we use for follow-up observations. In this slide, I wanted also to point you to the, there is a pointer, but I will not use it. I would like to point you to the volume that we are currently dealing, and we will be dealing in the near future once LSST comes online. Currently, we are observing a couple of thousand microlensing events per year. This is the number of events which can be covered by wide microlensing community, with 150 anomalous events and 15 planetary events per year. However, once LSST comes online, this will be increased 10 times at least, and we will be dealing with 100 planetary events and 1,000 anomalous events per year, which is something that the microlensing community and the community at large cannot cover. That's why we need target and observation managers to automatize our research. ZTF is an intermediate step between those two, and it has already been proved to be challenging in those regards. This is what we are planning to use with LSST follow-up. First of all, in order to fully uncover the data sets gathered by LSST, we want to do a full characterization of microlensing events. This requires consistent coverage of the event. We need to cover anomalies, which are short. They last from minutes to hours. We need multi-band photometry to use the full capabilities of LSST, and we For galactic plane events, we will need all additional information we can discover for these events, which is the source distance, the type of the source, extinction, and so on. In the galactic plane, we will be definitely dealing with less clouded fields, but this also means we will have less microlensing events. And we do not know, we cannot assume the distance to the source. And unlike this, in galactic bulge, we can assume that most of the sources are in the galactic bulge and in the center. However, we will be dealing with an extremely crowded field, and there will be extinction to take care of. And this is our setup of our project. We are currently tracking two types of events, which is the short duration events from planets and from dwarfs, and long duration events from candidate black holes. We are conducting photometric and spectroscopic follow-up with photometric to cover the light curves better, and spectroscopic follow-up to get additional information. Because microlensings are transient events, we need to constantly update our system. And once LSST comes online, we will no longer be dealing with events that come down to like 19, maybe 20 magnitudes. We will be dealing with events going down to 23 magnitudes, and sometimes they will jump up to become extremely bright. This means we will have to conduct coordinated follow-up with a wide range of diameters of our facilities, and it will have to be programmatic. That's why we designed the algorithm running below the hood of our target of the observation manager called MOB, in a way that, well, everything in red, in the red box in here, is done automatically without human intervention. I mean, a human can intervene, but doesn't have to. So we automatically download information from the surveys. We do automatic classification for Gaia events for now. We model our microlensing events without human intervention, and also this information is then used for target selection and prioritization. And then this information goes back to observation submission. Then we push this information towards any telescope we have access to and interface for, and maybe other facilities that are also interested in following up on our targets from our network model. These are some examples, and I will just skip over them. You can click them and check the papers about them in here. And I will go to the lessons that we have learned from this project as a pathfinder for LSST follow-up. So first of all, because of the volume of the information, we will need target classification. There are many contaminants. I'm not sure. Sometimes it's hard for them to be classified while the event is ongoing. Sometimes it's hard for them to be classified while the event is finished. Will this classification be handled well enough by brokers, or will we have to implement some additional methods? That is a question to be answered and understood. Another thing that we already have noticed is extremely important, which it is the automatic target selection and observation submission. Even with the current surveys, we cannot handle the workload which is necessary for that. Additionally, we need to accurately model our microlensing events because we are using the current information and best fitting models for target prioritization, so it has to go in a constant loop. And finally, we need to, we recently discovered that follow-up information, because the microlensing observations have to be so dense sometimes. There's a lot of images and we need storage space. So this is actually a thing that we have to be mindful of, especially once LSST comes on, starts producing alerts and information, and we will have way more microlensing events to cover. There's also a question of additional information in the galactic plane, which I don't have an answer for right now, but maybe we will be able to bridge it with current or upcoming surveys. So I will stop here. I can jump into the last slide that I have for this, and I will take questions. Okay, great. Yeah, sorry, I didn't.
Yeah. So please write down your questions. Don't forget them, and we'll have a Q&A at the end of 4 5. Our next speaker is Natasha.
Hi, my name is Natasha Abrams. I'm a
Start sharing again.
She's sharing on Zoom,
Sorry,
so yeah.
Yeah. My name is Natasha Abrams. I'm a grad student at UC Berkeley, and today I'll be talking about microlensing in the era of all sky surveys. First, an update on how we've been looking at microlensing in Rubin, Cadence, like SCOC. Update on that, and then going into ZPF microlensing and lessons that we can learn from that. So Katarzyna gave a great introduction on what microlensing is. I'm going to delve in a little bit more on some of the observable quantities that we can use in microlensing. One is the Einstein crossing time, or TE, which you can think of like the duration of the microlensing event. That scales as the square root of the mass of your lens. It also is inversely proportional to the relative upper motion between your lens and source. There's also the microlensing parallax, or pi. So over the course of the year, as the Earth goes around the sun, we'll be observing the microlensing event from different angles. This can lead to bumps and asymmetries in the light curve. As you can see at the bottom, there's the red has the least parallax, the purple has the most, and you can see those bumps and wiggles. And pi is inversely proportional to the square root of the mass. So with those measured and with the galactic model, you can go through and start to identify black holes, or in general, probe the masses of objects that are your lenses. So here is a plot of pi e versus PE, where the red squares in the bottom right are your black holes, and they start to separate out in that space. So by its nature, microlensing occurs in crowded fields. You need a chance encounter of two objects going by. So here is a little video of a microlensing event over the course of a few years from the oval collaboration. And this is actually a black hole that we measured with microlensing. So if you're looking at photometry alone, you need a large survey in order to both find black holes and probe stellar and galactic quantities. So in Rubin, we use a few different metrics inside the metric analysis framework in order to probe how well Rubin is going to do with microlensing and evaluate the survey strategies. We have a few different metrics. So one is a detectability metric. Do we even start to detect the microlensing event? That's just 2 points above 3 sigma above the baseline, and some characterization metrics. So one is, do we have at least 10 points within plus or minus 1 Einstein crossing time? Then in a bit more detail, so we can look at the Fisher information matrix, which is the inverse of the covariance matrix. And so that will tell us how well we can characterize particular parameters, such as TE, the uncertainty of less than 10%. The population of objects that we inject are evenly distributed, or the density of events is distributed as the number of stars squared from the Tree-Legall map, and we use a baseline magnitude as the mean Tree-Legall map with magnitudes there. So if we zoom in a little bit more on the Fisher information matrix, so outside of the context of the map, since the stuff in the map needs to be super lightweight, we go deeper in a few different options where we include microlensing parallax and TE characterization using the Fisher information matrix. We take a representative bulge patch and a representative disk patch and simulate 100,000 events using Bagel, which is a microlensing model, and fitting code. So first I'm going to summarize some of the results from the 3.2 of the options and earlier, and then I'll go a little bit more detail into some of the more recent options. So just in the first order, focusing on high stellar density areas, such as the galactic plane and bulge, the most significant impact on microlensing. If you don't look at the galactic plane and bulge, you don't have a microlensing survey. But for a while now, we've included that as part of the survey. And so also, Rubin is going to measure the stellar and black hole populations as a function of place in the galaxy. So as we started to add events, as we started to add points throughout the plane, that decreased the characterization efficiency by about 10 to 20%. But using Rubin's unique capability to look throughout the plane, we think is a huge scientific advantage. There's also the concept of rolling, whether, which hopefully most of you have heard of, but if you 1 year focus on one part of the sky and then another year focus on another part of the sky and alternate between those. And rolling needs to be done carefully in the bulge, if at all, or in the bulge and plane, if at all, in order for microlensing parameter characterization to occur. I'll talk a little bit more detail about some of the synergies with Roman, potentially like some very light rolling, or in general, like severe rolling to optimize that we don't have too many large gaps for the both of the microlensing events. So first I'll be talking about the high blob. So I don't know if you can see my cursor. This little blob up here above the bulge. So there's the question of whether that should be kept or if it should be moved so that there's like a more contiguous area throughout the bulge and rest of the plane. And so the removal of the high blob includes some detection. First, I'll explain how to interpret these plots since they're super information dense. So on the y-axis, we have broken up the sky into pencil beams throughout the plane, the galactic bulge, Magellanic clouds, the rest of the galactic plane, and then combining them all. On the x-axis are various opsims. The color in this case is how what fraction of the events were detected. And on the left are 30-day microlensing events, and on the right are 200-day microlensing events. And so the brighter the color, the better it's done. And you can see, especially in the right-hand plot, in the no high blob case, that we have an increase in detection. We can also now look at, these are the same sort of plots, but for the characterization of events. And so you can look, especially in the left-hand plot, there's that really bright spot where you have the Roman V 3.3. So that basically, you take some small fraction of the events, put them on the Roman galactic bulge time domain survey field, and you see a large increase in the characterization of events. And that's not even taking into account potentially joint processing the data and having great increase in the quality of the data. So we can also look at how rolling strategies are treated. So the way to interpret these plots is that this is the microlensing parallax. It's a function of the Einstein crossing time. We took two strategies. So there's the Milky Way roll bulge divided by the baseline 3.3. The redder it is, the better the baseline did. The bluer it is, the better the rolling strategy did. On the left side, it's a bulge field. On the right side, it's a disk field. And on the bottom, there's just a, that's the representation of how the pointings look in those particular fields. So on average, there was a 7% increase in characterization in the bulge field and 20% in the disk field. So that's it for Rubin for now. Now the question is, when we did ZTF microlensing, what did we learn that we can apply when looking forward to Rubin? So originally we found 60 events, 19 of which were outside of the galactic plane in the first 3 years of ZTF data, 28 of which overlapped with the Rodriguez et al. Sample. So on the left side, you can see the points that we had after our level 5 characterization, which is basically that we went through, made some quality cuts, did successively more complicated microlensing fits, and got to the end. Then on the right side, it's a little hard to see, But those red plots are those that made it past the by-eye inspection. There were about 1,000 points at the, sorry, 1,000 events at the level 5 stage that we had to go through by eye. And so, you know, one question when we get to Rubin, we're going to have a lot more events. How is that going to, is it still going to be feasible to have this sort of by eye thing at the end? How can we improve it so we can minimize the number of events that are going to be at that stage? We can also look at the TE distributions, which is a good metric on how a good measurement of the your microlensing events. And you can see that we have good agreement in the shapes between our simulated versus oval events, which is the ground-based survey, and CTF events. So we actually found overall fewer events than we simulated. So in the bottom plot there, you can see the total number of events as a function of the faintest magnitude of that event. So the purple is the simulated, the red is what we found. So particularly at the faint end, but overall we found fewer than we expected. There's a few reasons for that, we think. One is that in the simulations, we didn't take into account these long seasonal gaps where the bulge is visible. Two, we found that we needed significant amounts of baseline, so T0 plus or minus TE at least, in order to characterize the events and to distinguish them from other things, variable stars, like that. And also it's possible that fainter stars are selectively removed by the algorithm. That's potentially due to the photometry. They're in crowded fields, there's a lot of blending. How you do the photometry needs to be done very carefully, which we'll hear more about later. So that's something to keep in mind. We're also investigating the nature of these out-of-plane objects, which I'm sure Rubin will find lots of too. So of the original 19, with additional data, 8 of them were revealed to be quasars. So the dark blue is at the point where we identified them as microlensing events. A few years later, the light blue, you know, a lot of them started to do these funny things. And so that's something to keep in mind, and you know, how potentially things with spectra or stuff like that could help us to alleviate potential contamination. So of the 11 remaining objects, we're following up for the brightest ones with split cast to probe their nature. Of those remaining ones, also 5 of them have Gaia parallaxes, so that's a good sign. That indicates they're between 0.7 and 4 kiloparsecs away. And the 2 of the remaining ones, interestingly, have SDSS redshifts, but they continue to look flat, and one of them is very close to a near neighbor, as you can see, so I might have confused it. But they also have Gaia parallaxes, so looking into what's happening there. So in summary, I'll just leave these up and emphasize that crowded field photometry is going to be critical for being able to extract the microlensing events from within.
Our next speaker is Anibal. Anibal, can you hear us?
Hello, yes.
Awesome. So can you please share?
Yes.
You have 7 minutes.
Okay. Can you see this slide?
Yeah.
Okay. So, my name is Anibal Varela. I'm from the Universidad of San Martín in Argentina. I'm doing my PhD with Martin Macler as my advisor, and this work is happening in the TBS microlensing subgroup. And as you can read, it's about the synergy in microlensing events observed by Roman and Rubin. So the Nancy Grace Roman is a NASA mission that will be launching in 2027 to the Lagrange orbit L2, L2. And one of the main surveys will be a planet search using microlensing. So the motivation about, for this work is combine the data of Roman and Rubin and when observe the same microlensing event to see what are the improvements in the characterization of those events. And this is motivated because Rubin will be look at the same region of the sky, and so and it will be and in the same time. So as Natasha and Katarzyna previously talked about the microlensing phenomenon, so just I want to add one more thing, that is that in this work we also look for microlensing, but with binary lensing, that it's a system where the lens is like, for example, the sun and Earth binary system. So when one observe the microlensing signal, can detect the presence of the planet and obviously of the in the signal of the sun. For example, here this little bump is the signal associated to the planet. So and one thing more is that since these kind of events that we study in this work are events observed by two different positions. One with this can use something called a satellite parallax to estimate the parallax in the system, and with that using the microlensing theory, one can break degeneracies and estimate the mass of the lenses. So this, since Roman and Rubin still are not making observations, and we address this study with simulations, we start using the trilateral simulation and for the sources, and obviously simulate sources in the Roman region, and using the opsims, we compute the scheduled observations that Rubin will make, and we have the information about the cadence of Roman and one approximately date of when will start its observations. So with this and the noise model that we can compute using previous works in about Roman, and the opsims and the noise model that we can obtain from the opsims, we can create light curves using Pylima software and the Koshimoto model for cinematic parameters such as the relative proper motion and the distance to the source and the lens. And with all this, we can create light curves as it was observed by Roman and Rubin. And with this, we can then, this is something like this, mocking data, and we can fit this, and we fit these light curves using the Pylima software, and the approach is fit one light curve using only the simulated Roman data, and then add the Roman and Rubin data and see what is the improvement. So we make that for several models of microlensing, one of those models is, for example, this binary lensing system associated to planetary systems. Then, okay, so you in these light groups can observe the model fitted by using the data of Roman and Rubin in blue, and the model using only the Roman data, and the true model, and all the points are the fake data. So to understand what are the improvement of this data combination, we use metrics like this, for example, like the ratio between the uncertainties of the parameters obtained from the feeds, and the ratio of the bias of the parameters of the microlensing parameters obtained from the feed of the light groups. And here we can estimate the fraction of events that reduce its uncertainties by adding the Rubin data. So, for example, for this set of events, binary lens events, we have the 60% of the events that improve its uncertainties and reduce its bias for a same time, that is the duration of the events. And we can keep looking into other class of events, like free-floating planets that are events with short duration, and look at the bias and the precision in the parameters obtained from the feeds, and see that and see where the improvement is more relevant, and we can and a final way to estimate this improvement is estimating the mass from the light groups and the feeds, and compare with the mass with the true mass. So a final comment is, for example, for another set of events associated to black holes, we can see, for example, that the precision in the estimation of the mass is improved in a fraction more large of events combining Roman and Rubin data. Here you can see that it's 53% of events have the precision and under 20%, and that is more than using only Roman data. Okay, so this is this work that we developed and in the Microlensing subgroup. So just these final remarks. The simulation is ready. We are exploring these metrics and focus on a specific subset of events to evaluate when this combination is more relevant. And okay, and I'm not talking much about this, but we're using one feature algorithm sometimes gives some issues when in the uncertainties estimation. So that is something that we should explore in the future. Nothing more. Thank you.
Thank you so much. And so please keep your questions in mind or write it down. The next talk is by Karen Nowogrodzki. Karen, do you want to start sharing?
Yes, of course.
You have 7 minutes.
Okay. Can you listen to me now? Don't you?
Yes.
Okay.
Yes, we hear.
Well, hello, I'm Karen Nowogrodzki. and I've been working on the insertion of my microlensing events in the P0 simulation with the microlensing subgroup. I'm doing my PhD with Martin Makler in UNSAM. So our goal is to understand and quantify the constraints we can expect to measure on the parameters and characterization of the light course by assessing the reconstruction of the light curve with the LSST pipeline. Because there are no microlensing events in DP0, we first need to simulate our light course and inject them. Then we extract the realistic light course with the LSST cadence and errors, and then fit them to obtain the parameters. And following this step, we aim to use the realistic light course extracted to test some variability classifier systems for early detection, like training a machine learning model. The objective now is to develop a tool to simulate a microlensing light curve with the desired model, magnitude, band, and location. And with location, I mean if it's an empty region, or it could be in on top of another source to test cases with blending. Then we inject and extract the light curve with the LSST pipeline and obtain the realistic light curve to be characterized. This is how the tool assessed this so far. In this example, I select the I-band, a random location with its sky coordinates, the microlensing model with its parameters. Then the tool gets all the single visit images, also called CALEPs, containing the location for the band. In the right, you can see 4 contiguous CALEPs with the limits in blue, and with their 5 sigma detected sources in green, and the injected point in red. Finally, here is the injected light curve in blue and the extracted one in red for the magnitude of 19 and a brighter case with 16 that I will show right now. Yes. So in the video, we can see the variability in time of the bright, more clear in the case with 16 of magnitude. Here is a simple test and study that was done, that is to inject a range of magnitudes. In these cases, we have for 23 and 24 magnitude, where we test the extracted light course approaching 5 sigma depth, which for the I-band is 23.41. And as expected, they have the greater errors. Meanwhile, approaching the saturation magnitude, we have pretty small errors, also as it was expected. So the future steps are to generalize and automatize this proof of concept by injecting the light course in an arbitrary position that is already done, while downloading the new injected CALEPs, working for all bands at the same time, using realistic distribution with trilegal simulations, using more realistic and complex microlensing models like on source, on lens, or binary or parallax, etc. Using PyLima, and use a realistic distribution of microlensing parameters. Also, we need to make it scalable to more CALEPs and multiple regions. Here we are having some memory issues yet, but we are going there. And we want to make the catalog and the true parameters, with the true parameters, sorry, and injected CALEPs available for everyone with everyone here with the butler. Finally, to fit the realistic light course and derive the constraints. And that's it. That was what I wanted to tell you.
Thank you so much.
Thank you.
Okay, so now we have time for questions. We have 10 minutes time for questions. Yeah, for people online, please raise your hand. And is there any questions in the room?
I have a question for Anibal. Anibal, have you already identified cases where Roman and Rubin's observations significantly improve event characterization?
Yes.
Do you have
I'm
some idea what kind of
I'm
events
sorry.
they are?
I'm sorry. Can you repeat the question?
Yes. What are the events where Roman and Rubin observations done simultaneously or in close succession? What are these events? When do they improve?
Okay. The answer is complex, but the events that I test that are improved are the black hole, the one associated to black holes and binary lensing. Binary lens, since the time duration is large, and improve in the those events are improved in the characterizations of some parameters of the model. For example, the binary lens system have a almost a negligible finite source effect. So that parameter is not constrained, nor not using nor using the Roman and Rubin data. So the answer, I think, is depend what parameter we are looking, and but in summary, those events with more large duration is the ones that have the parameters better constrained, combining the data. So not free floating planets, for example.
Are there any other questions? I do have one question for Katarzyna. If if new people, with new observers want to get engaged with the program you're developing for the follow-up observations and microlensing systems, what are the steps they should take? How should they get involved?
Well, if they want to work with, use MOF as a place to look for microlensing events they want to observe, they can contact us. Well, through TDS channel, for example, and come to us, and then we will point you towards the web page and show you everything. We can also build tools that can help you help you facilitate your work, especially target selection, for example, which are observable from your side. It has been done a couple of months ago for the team from Argentina observing with LSST. So now they can go to target selection page. They click, they select the observing date for the night they have, and then they can select find their they receive a list of microlensing events they can select with important information. For example, what is the current magnitude and what's the baseline magnitude and what's the priority. So that's one way. Another way, I don't know. I mean, it is probably also not if other teams want to build their own target and observation management systems. We can also help with that, because LCO is has built one toolkit to do that, and we can provide some information, and we will be happy to help building any other tools that can, for example, submit automatic observations, or help you do that on your own, to submit automatic observations from your toolkit if your telescope has an API or something. I think. Sorry, Lindy.
No, that's all true. Yeah.
Thank you so much. There any other questions? Any questions on the Slack or? Okay. All right, so we can move on to the next section. We have a talk by Colin. You wanna?
I'm looking.
Yes. Yeah.
Good one. Okay. So hi, I'm Colin Slater. I'm the Deputy DM Subsystem Scientist. I'm going to be talking about image differencing in crowded fields. I see that Eric Bellum is online. He is the alert production science lead. And so Eric, feel free to jump in if there's anything you want to comment on any of these. So I'm going to talk a little bit about status to kind of bring everyone up to speed on where we are. But I'm also going to try and spend most of the time talking about where we're going for the next year, because we're going to get data. Let's talk about what we should actually do with that data. So we're going to talk about commissioning as well. So if you've been to these meetings, you've probably heard me say these few statements many times before, but I need to make sure that we're all on the same page here about what are the requirements on the data management system from the sort of construction era design documents versus what are not those requirements. So we are committed to supporting image differencing across the entire survey footprint, including crowded fields, including deep drilling fields. Wherever we're going to go with the telescope, we will try and make image differencing work. That is our high-level requirements. It's important to say that we don't have a requirement on direct image photometric completeness, not doing image differencing in crowded fields. So if we're talking pointing at the bulge and trying to recover all many 100,000 sources per square degree, that is a best effort endeavor from the project standpoint. We certainly want to recover as much of that geometry as we can. We've put a lot of effort into trying to figure out ways to kind of optimize that, but it's not the same type of thing that we're on the hook for with the funding agencies as we are for the image differencing. So overall, we should think of image differencing as a thing that we guarantee, and direct image as a thing that we consider to be best effort. We're talking about microlensing here, and we're talking about objects that vary. And so we think that because image differencing is a way to kind of remove all the things that's not all the objects that aren't varying, that's a way to kind of turn the crowded field problem into an uncrowded field problem for things that are changing over time. So kind of to that end, the highest priority in terms of development right now for data management is to ensure that we have functionality that supports that image differencing over the entire field. So we can't just run the image differencing immediately before we've done astrometric calibration, photometric calibration. We kind of have to have those basic image processing steps working well throughout all of these crowded regimes. Otherwise, we can't even get to image differencing. So that has been sort of the step one to making sure that we're functional in those fields, is make sure that we can do astrometry, etc. There's a sort of a handful of things that go into that. We do have requirements in completeness and purity. In general, they apply across the whole sky. There's some sort of detailed caveats on that, but those are goals that we're aiming for even in crowded regions. Sorry, for image differencing, completeness and purity and image differencing. And the alert production team has been doing testing on making sure we can run through these crowded fields. The most recent round of that was around 2020. And we recognize that sort of it's time to do that again, to update our testing now that the pipeline's gone through a sort of phase of kind of reorganizing some of the inner workings. We want to make sure that we're still performing where we want to be on these fields. So there's a great tech note, DMTM 171.lst.io. This was led by Ian Sullivan on the alert production team. This is what the testing that I was talking about, where they took decam bulge data, ran it through the LSST pipelines, and then did all those adjustments to make sure that astrometry is working, to make sure that photometric calibration is working. All of that adjustments in order to get to doing image differencing. I'm not going to go deeply into all the details of that report because it is very long, extensive, lots of great pictures. I encourage you to check it out. The bottom line that I take away from this is that the pipelines are working in these fields. There aren't fields that we've just had to abandon. So we do think we're being successful there. I just showed a picture of the little subset of one chip, the direct image and the difference image. The difference image, like you see, there's still structure there. Like there's clearly residual that we'd like to handle. But by and large, you can see that that does get us into the kind of uncrowded regime. Think of how many stars in the top image, how many of them are gone from the bottom image. It's a big improvement. That gives us a good handle to start characterizing those sources that remain. Yeah.
What's up with some of these sources that are darker in the center and then have these bright?
Some of those you can tell are saturated. I don't know that all of them are saturated. I don't have a good answer for the rest of it. So, okay, that was really all I was going to say about the test that's been done. Again, please check out the document and I can answer more questions about that if you like. So let's talk about commissioning. So I do want to, it's clear that it's a high priority of the project to collect data that tests in all parameter space, including crowded fields. There's just so many uses for testing in the whole range of levels of crowding that we're definitely going to take this data. I want to emphasize this will be part of the plan. Some background on how this commissioning plan has been built up. So about 2 years ago, I believe, the commissioning team started to ask people to kind of on the project to write sort of mini proposals, just to say, okay, what is the data you need? How much time does it take to observe that data? What filters do you need? What constraints do you need to, what constraints are on that? So we can kind of start to build up all of these different needs for the data sets to do tests on. And then now the commissioning team is kind of in the process of taking those, okay, now let's form that into a real actionable plan. This team needs this type of data, this team needs this type of data. Okay, what does that translate into real pointings on the sky? Can we satisfy different needs altogether? Do we need lots of different programs for observing? That's what the commissioning team is sort of in the, that's the phase that the commissioning team is in right now. I'll show you a little detail on the next slide. Just one bullet point here is that a lot of these crowded field tests, in general, we're kind of agnostic to where they're pointed. So as long as we're getting high density, that's the thing that lets us, that's sort of the basic criterion for being able to do some of this testing. But we're happy to allow other use cases for that data to kind of piggyback on that collection, that data collection. And if there's particular fields that would enable testing for you, and if we don't point at those fields, then you miss out. Then if it's feasible, we're happy to kind of adjust to meet those needs. So there's all sorts of places where we can kind of get feedback that will let us optimize the data, not just for the project needs, but for the community's needs. This is just I took one of Eric's proposals here just to give you a flavor of it. So what is our goal? We want to test performance of difference image analysis and high density fields. What are the other goals that we can achieve with it? What are the prerequisites? How much data? These are just the type of things that we've gone through to kind of make sure that we're collecting all of the required data for the commissioning process. I'm just trying to assure you that we are collecting plenty of crowded field data in commission. I'll give you one reminder, which is about the data previews. So it's been said a few times, but data preview 1 will just be ComCam. Data preview 2 will be the LSST CAM survey data. ComCam is, we're not guaranteeing a huge block of time observing with ComCam. So I think if you're really thinking about at what point are you most likely to get a large set of data that you can do your testing on, think of DP1 as a time where like it'll be a bonus if we get lots of good crowded field data there, but we're more likely to get it in DP0 than 2. That's just when we're going to have a bigger camera, more time on the sky. We're more likely to cover more science cases that will be useful for your science. So DP1 is a bonus if we get lots of time with it, but DP2 is where I think we get lots of data. One important thing to remember is that the data previews aren't the only routes to getting information during commissioning, to getting actual data that you can use. So alert production is going to be sort of ramping up in before DP2 is released. And we're going to try and ramp this up as soon as it's technically feasible. There's lots of caveats to what that ramp up is going to look like. Like we said so many times, we need templates. We might not be able to do it sort of on the spot. We might have to do it kind of offline next day. There might be delays. We might not be able to provide quite so much ancillary information. We won't have like the full data release to go along with it. So you might sort of have the alert and just the alert, or the alert and maybe some other data that we'll be able to provide. So this is something where we can't guarantee that like everything will be perfect right out the gate. It's going to be a slow ramp up process, but we'll try to get those alerts out and available to users. One note about these alerts is that because we're taking images so quickly, bulge fields or dense fields are places where it just might take longer to process those images. And at some level, we have kind of a fixed number of computers in the data center. And if we take a bulge image and it's going to take an hour to process, we gotta kind of make room for other data to come in and get processed first. So part of the ramp up process is going to be understanding how do we deal with fields that might take longer to process. Sort of crowded bulge fields are sort of high on the list of candidates that might apply to. We'll try to get a good solution for that. We definitely have levers that we can tweak to try to optimize the pipelines differently for these crowded fields and the uncrowded fields, but it's going to be part of that ramp up process. We'll try to have a catch-up process that still gets data from those. It just might be it might not be in 120 seconds. It might be a day, 2-day time scale. And last thing I just want to mention about alerts is that this is all going to come through the brokers. We're going to be ramping up the brokers at the same time that we're ramping up the alerts themselves. So they'll be your primary venue to get that data. So I put just a few sort of questions, topics, thoughts for discussion that I had here. I think the alerts is something where some effort, like if we put some effort in now to thinking about what will let us make the most out of those alerts, like that will help a whole lot when we get this sort of alert stream starting to flow. So I think advanced planning really pays off when we're talking about alert streams coming from the telescope. I also think it pays off to think about what is the other data that we want to have ready to go. If we have that ready, if we have sort of a plan in our mind for, okay, we got this data from the LSST, we want to compare that to data we got from this other telescope, this other survey, having that ready to go is going to make us more able to take advantage of that. It'd be great to think about what actual targets are going to help us verify your science. What is the best way to not just verify photometry in general, but to think about how do we verify that we're getting good microlensing results from the data? Are there tests? Are there confounding factors? Are there contaminants that we should start thinking about? Maybe the right thing to do is to think about, okay, how do we get the contaminant level low enough that we can get good microlensing events and we're not swamped by some other type of effect. So just think about those ahead of time, so we know how to be characterizing that data. And last thing is that I think we should always think about easy problems first and harder problems second. So let's make sure that we have a way to characterize the basics where we can kind of prove to ourselves, okay, this is working how we expect it in the easy part of parameter space. And now let's go expand that. Let's go push it into deeper fields, more crowded fields, dustier fields, high air mass fields, wherever you want to go from there. The project will basically be taking the same approach. We're going to do the easy testing and then kind of get harder and harder and harder. So that's really all I had here. I'll just summarize that like DM is testing in crowded fields, commissioning is testing in crowded fields. We have plans to make this image differencing available through the data preview and the alert stream. And I'd be super interested to hear feedback on validation tests for microlensing that would help you all get science out of that data stream. So thanks.
Are there any questions? There's a question over there.
Yes.
Yeah, so I think when you do the image subtraction, how much of it in crowded fields like the bulge, for example, how much of a dynamic range do you get for completeness? Because if you have a 1% error in fitting, a 1% residual, say, the full dynamic range from the brightest unsaturated stars to the faintest things you might be able to detect, something like 10 magnitudes. So a 1% thing is gonna, from the bright stars, is gonna be, I mean, you see what I'm getting at. Yeah. So the completeness issue is, in my mind, not, that as you get faint, you will not get as complete because you'll be fighting the residuals of brighter stars. And so it depends a lot on how crowded you are, what the IMF is, and and that sort of thing. So I'd be happy to run a comparison test if we can set something up like that. Mm-hmm. Doing it, with your method and doing it with running catalog things with crowded field code.
Yeah, I think that's definitely something that we've sort of come to realize more lately in these tests, is that like that sort of 1% residuals from bright stars really do matter. Like it's not the same as having blank sky background where you're just trying to chase faint things. And so I think we're still kind of processing how to incorporate that type of that effect, how to characterize that when we're doing the tests like we described there. I don't know that I have anything more elucidating to say on that. I know Ian Sullivan has maybe been in contact about doing some.
Yeah, he's not here at the meeting, unfortunately.
Yeah, exactly. But I think yeah, he's the right person.
And I'm volunteering.
Okay.
So
I will
help with any comparison or test.
I'll make sure Ian gets the message. Thanks. Yes.
With regard to the alerts and it might not be in the 120 seconds, it might take a day or two. First off, did you mean that in general or for kind of ramping up time? And if it's for the in general, if it takes a day or two to process, well then things that would be alerted get fed into the alerts team, or would it be kind of lost?
Yeah, so we don't want anything to get lost.
Yeah.
That's we do even if the alerts get delayed, they're still going to get into the alert stream. And I suspect mostly that would just be we'll do that processing once the sun rises and the computers are free, and then we'll have plenty of time. So it's not like it's going to take a full 24 hours of CPU usage, but it just might be alerts that happen early morning rather than at night. As for ramp up versus steady state, I think we should sort of, when we're thinking about brokers or downstream analysis systems, you should sort of design them defensively that they always accept the possibility that they might be getting alerts during the day, right? It might just happen because we need to do the processing of images in the night that are taken in the night. So that possibility is always there. I think the ramp up will be us trying to minimize the number of times where we have to go to that mode. So hopefully we'll be able to get as much done in the night as possible and a bigger fraction each night.
Just thinking perhaps more generally, the microlensing, which might side effect this problem where, you know, the things that you're detecting are infinitely faint at either end. To some level, don't you need to put a lot of difference imaging back on an absolute scale? So you have a difference, you need the first image to add that all back together again. So for some problems, don't you still have to solve to some level crowded fields in the original image?
I was thinking of this as I was watching the talks in the session.
Microlensing it might be okay for because the thing is faint, up it goes, down it goes again.
Yeah, I should have put a bullet point about that, which is that I think all these science cases, everybody's image differencing cases have sort of different constraints on how much they care about the AC signal versus the DC signal, and to what extent you really need to put those together, or to what extent you can get by just on the AC signal, which we will sort of trust to be more reliable.
Better, yeah.
Or if at least on a per visit basis. And if it's not, if we really do need that DC signal, then we've got to think more about how do we extract that from crowded fields where like seeing is changing, and so the amount of crowding is changing, that sort of problem. I think that's something where like this is really a science case specific discussion about like what are the validations.
It's almost something for DM to communicate back to all of the different people to say, tell us how much you care about. I like the AC/DC analogy. You need to know who cares and how much they care.
Right. And to some extent, I can't like the only solution DM has on offer are the things that are in our requirements. So if you say I really need the DC, for my first slide applies.
Sorry, no, I'm going through a tunnel. No, sorry, the
Exactly.
dropping.
But maybe in terms of how do we do testing of ways to get that signal back, that's something where we could definitely collaborate on.
I have two questions. So one, you said that it's not yet clear exactly what crowded fields will be covered in commissioning, or is that
I believe that's true. We will take so many images, like this telescope is so fast that we're going to cover a lot of fields.
Okay.
Very quickly. So it's not that we're not trying to like plan Hubble commissioning fields. That's a different regime. But yes, we don't have that set in stone yet. I think it is something that we're open to suggestions for. Like these areas are kind of key to science because we have this ancillary data, or because it supports the science case.
Yeah. Okay. So one other question about giving you feedback. Is this going to be? I mean, do you have like an official process in which like we will reach out to different groups for feedback, or do you want us just to write down our feedback in terms of like the questions that you ask and send them to you? It's like, do you have any?
Yeah, right. I realized that I forgot this bullet point. This is really a question for the commissioning team, and I didn't get a chance to ask them to have this answer ready for you. But we should find the commissioning team and make sure that they have an avenue to get that sort of more detailed suggestions.
Yeah.
But off the top of my head, I don't remember what that is right now.
Okay.
They periodically put out calls for commissioning input. The last one was a while ago. I'd have to go check with them to know what is their latest sort of venue for that input.
Who's the main person to contact?
I will try and go find Keith and get him to answer that question.
And you have some, is there any questions? Have some questions that we collected later. Like one question that how will field rotation affect the quality of DIA given its impact on alignment and noise?
Our expectation is that we should be insensitive to camera rotation. This is not the survey, the type of survey where we're like taking a template and then making our science image line up exactly. We are making a template that is a combination of many images that have been done with all sorts of rotation. And then we will take the difference image and actually warp it to that template to be different. So we don't expect that to be a problem. It's a thing to test, but we're not planning to have trouble there.
Like a follow-up question now, like in, the critical routine where like, if rotating it is changing like, the PSF or the distortion, and then like it might be like objects might be blended more with some of the other like nearby neighbors or less, right? With that in mind, do you think there's still not really a problem, or is it like maybe not?
So the way the image differencing algorithm works is it computes a matching kernel, which is supposed to take into account the difference in the PSF from this point on your science image to that point on your template image. And that matching kernel is spatially varying. Like it always changes because you could have different PSFs across the image, or you could have rotation and different amounts of blending. So that has enough flexibility that we expect it to be able to soak up most of that difference.
And so will there be any astrometric correction applied to the locations of the aperture locations? These might include differential atmospheric refraction, achromatic or chromatic.
Yeah, differential chromatic refraction is a whole separate talk. I would have to go get Eric or Ian to answer if they want to put any updates out about differential chromatic refraction. It's a detailed topic. I'm not going to be able to answer that one off the top of my head.
Sure. And will there be any ability to query or prompt for PSF feeding like DCF has for specific targets?
PSF. There's a force photometry service. Is that the same as PSF fitting?
I don't know what the question is, but it might be. So
Probably.
Probably they meant the force photometry.
Yeah, the idea is that if you have a point in the sky where you think there's a source, because either you see hints of it, or you have other information, or you just want a measurement that's done on, like literally this art deck. The idea is that we will provide a force photometry service. They'll go back and do measurements on that point, as if there was a detection there, even though there isn't. I think that's what they're getting at. I think that's what we have provided.
Follow-up question on that. Is there a limit to the number of objects you can do with that?
There's going to be computational constraints. There's going to be constraints of some sort. I can't tell you what those constraints are going to be, just because we won't know until we actually see what usage is like from the community.
But also don't forget that you don't just have to use the Rubin things, there will be IDACs as well, who will be perhaps offering more tuned services. So there may well be one of them offering dedicated compute resource for force photometry. I think the IDAC session was yesterday, annoyingly, but that's already happened.
Yep.
Okay, I think we're done with the questions here. Is there any final questions online or here in the room? If not, we can thank Colin again. Thank you so much.